I am Mike Brim from Oak Ridge National Laboratory. I recently transitioned. I was primarily on the research side of the house for quite a while, and I just recently transitioned fully into the production side, which is the National Center for Computational Sciences, and particularly the Oak Ridge Leadership Computing Facility. So today I'm going to be giving a relatively high-level overview of HPC storage systems, and there's basically three goals for this talk. I want to introduce you to the various types of HPC storage systems and their intended use cases, and then survey widely used HPC storage systems by those use cases and their associated architectures. And then at the end, I'll briefly get into how HPC storage is evolving and what the potential implications for users are. So to discuss the types of HPC storage, the first thing I'm going to do is briefly cover the data lifecycle. I'm sure you've all seen this before, but it's interesting to point out. And then I'm going to go into the specific use cases and their associated architectures. And then I'll give you some terminology that might help you think about things. So first, DOE computing facilities have to support the full data lifecycle. From data creation, storage, use and access, sharing, archiving for later use or for posterity, and then you can either take the data, transfer it somewhere else, or destroy it if you feel it's not useful anymore. But when it comes to storage, creation and access characteristics are really what dictate what type of storage you use. And facility policy often dictates where you can create the data. But there are also a lot of important characteristics, and this is not an exhaustive list, that dictate what type of storage you should use for data. Particularly total data size, the size of data you actually work with at a given time, the working set size, the number of processes that create, write, update data, the number of processes that access that data and use that data, and then particularly I/O access patterns, concurrency and frequency. So I highlighted a few of the common patterns here. So producer-consumer assumes that someone creates the data, says I'm done, and then consumers come along and can pick that data up. Bulk synchronous I/O is basically organized as distinct write phases where parallel processes work together to write some data. There's an application level synchronization, and then the readers say, hey, I can access that data now and move on with my calculations. And finally, what I would call what POSIX supports, which is free for all. Everybody does whatever they want and nobody synchronizes. And you should not ever do this on an HPC storage system. So please don't. So I like to use the colloquial names for HPC storage to describe the use cases. And this has a high correlation with what you find on the facilities help documentation for storage systems. So first off, there's software. So this is basically software that's managed by the facilities to run the system and applications. So this is system and user software. So you can have pre-installed system resource management software, application software, libraries for I/O management and for math, for example, and then system configuration files, the parallel resource runtimes and programming models, compilers, et cetera. Another use case is what I'll call home. And a lot of people call it that because that's just a Unixism. So this is your per user or per project space where you keep all of your application code, your compiled executables, the data that you use for inputs and outputs of your applications, your job scripts that you use to run your applications, documents you want to share within a project or whatever. And then we have Scratch, which is what Phil was talking about before with the parallel file system. So basically, this is the high-performance storage system for runtime use by jobs and parallel applications. And finally, Archive is where you put your data when you know you want to keep it and you know you want to keep it for a long time. And this is primarily for archival purposes, for meeting DOE mandates, for example, and also for sharing purposes. Now, the thing to point out for each of these use cases is they all have different requirements in terms of lots of metrics. So there's different requirements for the amount of space you need, the security and access controls and sharing that you use, how long the data lives, and then how the data is accessed, including the patterns, the individual I/O operations, the concurrency, the number of things that are accessing the data at one time, and the performance you can actually expect by using these different storage systems. So here's a table that runs through my worldview, and this may not match exactly with what is provided by facilities, but in general, we have the use cases in the first column, and then the metrics across the top. So, software is, in comparison to other things, a relatively small amount of storage that's necessary for keeping the facility managed software. So you don't really need a whole lot of storage space, and users don't really interact with that very much. It is long-lived, though, because the application and system software has to live as long as the system does. Obviously, there's data sharing because all the applications are going to be using the software. It doesn't have very high performance in terms of throughput requirements because you basically just update software every once in a while to fix bugs or provide new versions. The latency requirement is, I'll say it's medium because you are going to be using this software on a regular basis in a lot of applications. And there is access concurrency, primarily in the form of read operations. You're not going to see a lot of concurrent write operations to that type of storage. User home and project home are very similar. The only difference really being that user is kind of private to the user, so you don't expect much sharing to go on. That's not to say you can't have sharing, because a user can run multiple things at once, and it's sharing its own data with itself. Again, this is primarily read-oriented access concurrency, and larger storage requirements that last for a medium amount of time. So on the order of months, project allocations. Some allocations can do multiple years, but for example, OLCF, you typically get a year allocation and then you have to renew. So for throughput, you need a decent amount of bandwidth, in the orders of gigabytes per second, and you can expect relatively, medium access latencies. So the scratch file system, the parallel file systems, these are what all the money is spent on. These are very large amounts of storage, in the tens to hundreds of petabytes. But they're only really intended for temporary short-term access, so on the order of days or weeks. Lots of data sharing. They're targeted at a high throughput, but as Phil mentioned, hero numbers are hero numbers. You need to do a lot of work to actually get your terabytes per second of I/O throughput. That's full system I/O throughput. That's not what applications actually get. So it's low latency, but only in comparison to the other storage systems. It's not low in terms of what you could see on your personal machine. And this is basically the only storage area where you're going to see lots of read and write access concurrency at the same time. Finally, archive. You need lots and lots of space to store your important data. So hundreds of petabytes. Expect to store it for years or perpetually. There is data sharing, but it's not much concurrency in that sharing. And due to the technologies used in archive systems, you typically have very, very high latencies for accessing data. And so basically, you put it there, and you only go back and read it if you're going to get the whole thing and, for example, move it somewhere else. So I'll move on to talk about some terminology that you'll hear HPC storage people use when talking about storage systems. So for each one of these pairs, I'm going to give you the definition. But this will give you some idea about how to think about HPC storage systems in general and their architectures. So first up, private versus shared. So private, your storage is used by a single actor. Shared means it's used by many actors. Now, this is all relative. So your point of view matters when you're thinking about private versus shared. So if your actors can be users or compute hosts or processes or jobs, then the same bit of storage, for example, storage that's private to your job, can be shared among the processes inside that job. So context, when you hear about a lot of these terminology, the context is important to pay attention to. Local versus remote. So local is easy. It's you access the storage through a path that's local to the machine you're running on. Okay, so I said it was easy. It's not really easy. The architectures are getting really, really complex, and we'll get more into that later. So your definition of what's a local data path may differ from somebody else's definition of what the local data path is. But historically, when we say it's local storage, it's I'm running here and it's mounted. I can see it here. I don't need to do anything to access it. And remote is, yes, I'm going to access all my storage via a network connection. So the data is transmitting the network. All right, centralized and distributed. This is another one that's pretty fuzzy. But for this talk, let's assume that when I say centralized, I mean you're a storage client, and to get your data, you need to go out and talk to a single storage server. So that's what I'm calling centralized. And distributed means I'm going to go talk to many servers to get a particular piece of data. Distributed can mean a lot of things, and it's an overloaded term. And you may hear me later on violate my thing that I just said. So serial versus parallel. Okay, so this gets back to concurrency. So serial is a single client accessing a piece of data on the storage at any given time. Does not necessarily mean it's the same process accessing a given data. You can have serial accesses by different processes. As long as they don't overlap in time, and those time scales can be fairly short actually. It's basically, you can imagine a sequential access pattern by a bunch of processes. As long as there's some application level synchronization going on that says one process will not begin until the other process is done, that's a serial access. Parallel means you're accessing the data from multiple processes at the same time, the same instant. And finally, single tier versus multi-tier. So this is another one that point of view matters. So in a physical system, a single tier storage system has essentially one set of storage devices. A multi-tier in physical means the storage system itself incorporates multiple types of devices, and they are organized in a hierarchy or a layered architecture where different tiers provide different performance. From the logical perspective, a single tier means I'm accessing one storage system. There's one storage system accessing. For multi-tier, that means I have access to a bunch of storage systems, and they may be layered, they may not be. It just means I have access to more than one. So here's a nice decision tree graphic that helps me talk about, okay, what type of shared file system am I talking about? So for example, if I say I have a hard disk on my laptop and I follow this path, is it local data storage? Yes, okay, so that's my local file system. Okay, I don't have a local file system. Let's move on. Am I talking to a single server? Is it centralized? If so, it's probably what I would refer to as a network file system. So this is just remote access to data over the network. If not, okay, so we're not central, so we're distributed. But does it support parallel I/O? If so, let's call it a parallel file system. If not, it's a distributed file system. Anybody want to play this game for Google Drive. Google Drive, is it local storage? No, but it is cached locally. Is it a central file server? No. Google runs everywhere. You may talk to one Google, you may talk to another Google. Okay, so does it support parallel I/O? No. Google Drive is a distributed file system. I'll claim that. All right, so we've talked about terminology and things that will help us talk about the types of HPC storage systems in current use. And I'm going to go through these use case by use case. So scratch storage systems are the parallel file systems or otherwise that are high performance short-term storage for runtime use. So there are different types of scratch storage systems. The most common, you've most had interaction with is the parallel file systems, which I'll talk about in a slide. We also have burst buffers and node local storage. These are all intended for high performance short-term storage. So parallel file systems. So I liked Phil's graphic so much that I took it for my own purposes and modified it slightly. So the goal of a parallel file system is to give you high performance I/O for a large number of concurrent clients. That's what they're designed to do. There are many production examples. The most common are Lustre, IBM's rebranded GPFS, now known as Spectrum Scale, which I will continue to call GPFS throughout the rest of this talk because Spectrum Scale is just too many words. And one that's not necessarily as popular, but it's been around a long time, is Panasys, the PanFS. So all parallel file systems have some shared architectural features that are basically key to what makes them a parallel file system. Although some of these things can get a little fuzzy as well. In general, the idea is you have your compute system. It talks through some number of what Phil referred to as bridge nodes, and I'll call I/O nodes. And it talks to a separate network where the parallel file system is running that has I/O servers and metadata servers. And these are separate things. The I/O servers handle management of blocks of data. Metadata servers handle namespace, file system hierarchy, file attributes, and clients will, when they, for example, open a file, they'll talk to a metadata server. And when they read a file, they'll talk to a metadata server and tell me and ask, where is my data? And the metadata server will respond, and the clients will then go and talk directly to the I/O servers to get that data. And so the separation between metadata and I/O servers is for a lot of reasons, but it follows the mantra of do one thing well. And so there are a lot of optimizations that you can make inside a storage system related to caching, caching of data, also caching of code that runs over and over in a multi-threaded service, where the things you do for metadata are very, very different than the things you do for accessing I/O block data. And so spreading these things and dividing up the functionality among them is a good thing to do, and most parallel file systems are architected this way. So the I/O servers, which there are typically many, help to balance your I/O traffic. So as Phil pointed out, different requests often end up going to one or more servers, and accesses from different clients often end up hitting different servers. And so the idea here is you have some amount of overall network bandwidth to your I/O. And in the best case scenario, you can use up all those network paths talking to all the different I/O servers, and you're going to see the full network bandwidth that you can achieve for your parallel data access. So another thing that has been around for about 10 years now, actually, is a burst buffer. So we take the picture we had before, where you have your compute system, and we put a new storage layer on what I will call the I/O nodes. And so the idea here is when systems get very big, it's possible that your parallel file system can no longer handle the load. And just as a case in point, you can fully saturate the Summit parallel file system's bandwidth using about 300 nodes. There are over 4,600 nodes in Summit. We've been at this for a while now, and we're applying Band-Aids in the storage community to try to reduce the number of requests that actually go to a parallel file system. So a burst buffer is an approach that does this. And basically, you just introduce this new storage layer between the compute and the I/O, the parallel file system, that buffers bursty writes. So this is pretty common in parallel applications in the form of checkpoints. So you can absorb these bursty I/O traffic. And then the idea behind these separate tier burst buffers is the write data will automatically drain to the parallel file system at some later point, while you have in your parallel application gone ahead and moved on to computing on your next simulation piece. Burst buffers are also designed to be able to cache data from hot reads. So this is portions of files that are accessed a lot in a short amount of time. However, the key production example of burst buffer system, the Cray data warp, which was deployed with Corey, it actually doesn't do much of this kind of runtime caching of reads. It's more about staging data prior to your job, and you can read it. But the architectural features of this burst buffer layer technology is you take faster storage, typically SSDs, possibly flash SSDs, and you just move them closer to the compute. You get the automatic data staging to and from the parallel file system in the background to help overlap your I/O with your compute. And the other thing is, these are typically reservation oriented. So when you get a job, you can ask for a portion of the burst buffer storage, and it's basically dedicated to your job. And that can provide some benefits in terms of reducing interference from other jobs on the system. In comparison to when everyone's accessing the parallel file system, everybody's using the same network to get there. So the final piece of scratch storage that's common today is node local storage. And this is found in almost all of the big systems today, actually. And the idea here is, let's go back 25, 20 years. This is what I would call disk full clusters. So basically, we've gone full circle at this point. We put, just like in your laptop. So imagine that your HPC system is just 10,000 laptops. That's the idea of node local storage. So everybody has their own local disk. The goal is the same. We're trying to reduce the load on the parallel file system by redirecting I/O operations to something that's faster. And in this case, it's really fast because it's local to the system. The downside is this architecturally is not a shared file system. The node local storage is only accessible to the things running on that node. So there's a lot of very smart people working on solutions that can make this stuff look like a shared file system. And then you also have to have special solutions for taking data that you put into this node local storage and actually pushing it out. It's not automatic in the terms of like a burst buffer tier. But it is fast. And an additional benefit is that if you have node local storage across all the compute nodes in your large HPC system, then that capability grows as you allocate more and more nodes. So theoretically, as long as you've arranged your I/O pattern in a nice way that separates all the data to be local accesses, then you can have linear storage bandwidth as you grow your jobs. All right, moving on to a different use case. Home storage. So again, this is for per user, per project storage. Some of the common solutions in deployment today are network file systems, such as NFS, distributed file systems, which are not parallel file systems. I'll talk about that in just a second. But it turns out that because there is a lot of sharing that goes on, even read sharing, many sites choose to use parallel file systems for their home storage. The picture I'm showing here is what OLCF did in the past and will do again on the next system, Frontier, which is we use NFS for our home and project areas, but NFS is not a scalable solution. I mean, you basically have a server and you need some way for lots and lots of clients to talk to it. And one approach to handling this problem is about 2012-ish, or maybe a little earlier, Cray, now HPE, created the data virtualization service. And essentially all this is a tree of caching NFS servers. And so you're just spreading out the load. At the root, you still have one file system that's served by NFS, but the DVS servers take portions of that's accessed recently, cache some of that data locally, and give you more things to talk to. And surprisingly, this has worked for systems of 18,000 nodes. That's probably about the limit of what it could do, but I call it a distributed file system because you're talking to many servers. For software storage, this is very much like project or home storage. The only difference here is the local file system. So again, disk full clusters. So in the beginning, when you ran Beowulf clusters for HPC systems, you basically deployed a bunch of individual nodes. They all had the operating system, applications, libraries, et cetera, installed on all the nodes. Well, that was bad for a lot of reasons, mostly management reasons. And so we moved away from that and made everything network accessible. But now that we have no local devices again, the administrators and operators are saying, wouldn't it be nice if we can use some of that storage to deploy software that's used often? So this is actually a win for users too, because it takes away a lot of those network accesses for commonly used software. So like the operating system kernel image and the libraries that are used most often, we can cache those on node local storage and get a lot better system performance. So this mostly affects the boot time of your applications themselves. And finally, for archive storage, again, this is for long-term data storage. The most common solution is to use a tape library. So if anyone's not familiar with how tapes work, it is a physical tape, like a cassette tape. I don't think I'm too old to assume that most of you have seen a cassette tape. So what that means is accesses are spinning a tape over, some magnetic reader. And so you can basically only do sequential accesses. You're not going to be doing random accesses or seeks very well in tape systems. And so this is really intended for, I'm going to write full data in a sequence, or I'm going to read full data in a sequence. This is why the access latency is so long. But they are very, very efficient at compact representation, and they have the additional benefit of their physical things that you can take and go store somewhere safe for later keeping. So basically, a lot of facilities will back up their tapes every once in a while, ship them off to some place that can't burn down. The most popular storage system for managing tape libraries is the high-performance storage system. So this is available at OLCF, ALCF, NERSC, probably pretty much anywhere they use tape libraries. But it's software that's optimized to make efficient and performant use of these things. And recently, it started going into the tiering and support for different types of storage media. So just a brief summary of the survey of storage at DOE computing facilities. So by use case, we can see that ALCF and NERSC went the parallel file system route for their home and software, whereas OLCF uses, tree of NFS and also node local storage for software. Scratch, you see GPFS, Lustre, burst buffers, node local storage, and everybody's using HPSS for archive. How fast am I writing? Yeah, that's not too bad. So HPC storage is evolving.
Yeah. Before you go too far, I have a question on the Slack about using those burst buffers at the local storage and how much or how little help the systems would provide. Can you say a few words about what, if any, facilities or services facilities provide users?
For the node local.
Yeah, staging in, staging out, or if you do it on your own?
So I can talk to what's provided from OLCF perspective, and then I can also briefly mention some of the stuff that exists in early form, not necessarily production. So one thing that OLCF provides for node local burst buffer is essentially free staging. So there's a library that you can load via a module called Spectral, which basically, this doesn't support parallel I/O. This is still only using local storage, but you open a file, you write your data, and when you close it, it'll automatically stage it out to the parallel file system in the background. So that's one solution, and it works well for file per process or anything that's just a single file or a group of files on a node. So the alternative, which most people would rather have, is a shared namespace over these node local storage devices. And so within ECP, I have personally been working on a project called UnifyFS, which basically gives applications the appearance that these node local storage is actually under a single namespace. And there's a lot of complex software that goes on underneath, and it's not going to be the same performance as a parallel file system, but at least gives you the ability to say, I have an MPI parallel application using MPI I/O, and I can run on it, and I can use node local storage as the place where I'm storing the data. It's not like Spectral is automatically, it'll stage for you. UnifyFS does not provide automatic staging, but it does have support for explicit transfers when you're done with your data. There have been some other work to do different things with the node local storage, but primarily it's job level integration to move things in at job startup and move things out at job end. I don't know. Did that answer the question for whoever had the question? All right, so let's talk about where we're going, not where we are. So first, some challenges. So exascale is here. It's official, top 500. So for 30 plus years, DOE HPC meant scalable modeling and simulation. This drove the development of HPC storage for that time period. Primarily, this was bulk synchronous checkpoint restart I/O. So this is all write dominated, mostly sequential. And parallel file systems, as we have today, are designed to do this well. And they also have this, nagging need to provide POSIX I/O semantics. But checkpoint restart for full-scale applications on an exascale system is problematic. Doesn't matter how good your parallel file system is. The number of components in an exascale system means that you will see failures, most likely on the order of every couple of hours. This could be a node level failure, it could be a failure inside the storage system. Something will go wrong. There are just way too many components. What this means is, in order to do checkpoint restart on an exascale system, you will be expected to do more and more I/O. You'll have to checkpoint more often. This means that we build a very, very, very big, very, very capable HPC system, and you're going to be spending more and more of your time not doing compute. That's not a good trade-off. The other thing, which I already talked about, is the clients that you can expect in large exascale systems fully exceeds what the file systems that are deployed alongside those systems can provide. So we can saturate parallel file systems with hundreds of nodes. We don't need 10,000 nodes to saturate a parallel file system. Challenge number 2, data-intensive science. It's everywhere. It is making things look bad. So what types of data-intensive science? So large-scale data analysis. So everybody's seen the new wave of Gordon Bell. They're all data-intensive, machine learning, large-scale training. This is all read-dominated, most times uses random accesses. This is not what parallel file systems are designed to do well. Also, we see lots and lots of experimental data from new instruments with very large data generation rates. So Large Hadron Collider, Square Kilometer Array, ASTRO. So basically, it's difficult or impossible to store all the data that these things collect in lossless form. Now, these particular sites have actually gone to the step of building data centers right next to the things where the data is collected so that they can try to store all this data. But the same analogy of experimental data being collected is widespread across lots of different scientific instruments. So neutron sources often have to do data reduction before any data is ever stored. We need storage systems that can accommodate such use cases. So we have new requirements for where we're going with HPC storage. In the area of interfaces and access patterns. So reads are now as important as writes. In fact, they're probably more important. And POSIX, stream-based file read-write, is almost never the right I/O semantic if you want to do a scalable HPC workload. So this gets back to the earlier question. Many workloads might benefit from alternatives, such as key value stores. So put get of objects. And you might want some object versioning in there to have some consistency semantics. So publish, subscribe. So this is the idea that there could be many producers and many consumers, and you might want to notify when something new has been put out there. Streaming data. So I mentioned the experimental instruments generating streaming data. So also, cloud space. Lots of AI ML comes from cloud space. So the technologies are coming from there. We're taking them and we're trying to deploy them on HPC systems. It's often the case that the storage system approaches that are integrated into these AI ML are hard to deploy on HPC storage. Cloud data abstractions. So again, key value or columnar. So this is, instead of a key and a single value, it's a key and lots of values. these are very good for data analysis based on queries. Queries are nice when you don't know what you're looking for, and that's becoming more and more common in scientific data analysis. So graph analysis is a particular form of data analysis where they've actually shown that if you build a custom storage solution, the representation of the graph and the storage system implementation to efficiently access nodes and edges, and you can get hundreds of times performance improvement by customizing your storage to support the workload. Analysis of real-time streaming data from many sources is very, very common in the public cloud. We could take those same ideas and move them into HPC space. In terms of storage technologies, this is more from the people who manage storage resources. So elastic provisioning. So if you're not familiar with what elastic means, it means you get as much as you need. You can grow and shrink the number of resources you're using based on your current work. This is something you get for free when you're using Amazon or Google or Microsoft cloud services. HPC, you get job allocations, and if you're lucky, you get some storage that's associated with a job, but not really. The other thing is quality of service or service level agreements on your I/O. So cloud has been doing this for several years now, and it would be really useful, I think, for users to say, hey, I really do need, my I/O is not super intensive, but I would like to have a minimum guaranteed rate of I/O read and write. So what are some of the architecture trends that are moving us? So the one that's most common right now is tiering for performance. So basically, we introduce as much fast, non-volatile based memory storage everywhere in the hierarchy. And some of this hardware is actually optimized for these new semantics like key value or put get. So we deploy these things everywhere in all the tiers. So there's lots more storage tiers that include this hardware. So let's start at the top. So we've already seen no local storage in the compute nodes. So what's that middle green layer then? So if the gray boxes or the gray storage is node local, so the green ones are what we call near node local. So the idea here is you can put storage resources inside, for example, a rack of a computer system, and it's still accessed by a local data path. You're not technically going over the network because they've actually designed systems where you can use the standard I/O bus to access things that are available at a rack level rather than a compute node level. And so El Capitan, the next Lawrence Livermore capability system, will actually have near node local storage. So we've talked about burst buffers in the I/O nodes. You can imagine within that burst buffer tier, you can have physical tiering of fast storage and disk storage. And then outside of HPC and parallel file system, HPSS, as I mentioned, is working to incorporate tiering inside their support. So basically, there's tiering at multiple levels everywhere, and how much of this is exposed to users is not at all clear at this point. Another interesting architectural trend is storage disaggregation. So the idea behind this is you basically directly attach storage to like your compute network, so your high performance network. And then you allocate these storage resources dynamically to predefined pools, which is basically just collections of storage resources. And then the pools provide I/O performance on blocks or objects. They don't do POSIX. You can assign these pools to jobs. Pools can have different requirements in terms of storage space or quality of service or whatever. But the idea is it's much more dynamic and it meets the needs of workloads more specifically. So, user advice. I don't know how many of you are thinking this, but I expect all of you. So it's all very confusing, and how do you expect us to deal with it? Okay, back to Phil's plug. Use an HPC I/O library. Use abstractions that map closer to your applications. For example, hierarchical groups of data sets, so that we can take all of this complexity and do something interesting with it that's completely transparent to you, but hopefully give you enough knobs to tweak it to meet your needs. And then there are vendor solutions that are addressing this. So we've already mentioned Deus. It's a whole new set of abstractions. And they're designed explicitly to manage this type of tiering, complexity, different use cases, different interfaces, while hiding all the low-level details of managing storage. With that, take questions. Yes, Phil.
Mike, we have one on Slack from Andy says, I'm using local or your notes where you bring stuff like that. We spend the first 30 minutes of my job for that. That may be a facility use anything on the problem, so elaborate that.
Yeah, I mean, if you're doing something that's read heavy, for example, I think the facilities can probably do better jobs of providing tools for certain use cases. I know LLCF doesn't have any predefined tools. For example, I want to take this data set that's multi-gigabytes, hundreds of gigabytes, and deploy it across all the nodes of my job on the node local storage. There aren't easy tools available that you can just call and do that. The technology is there. We have ways to do that transfer, but you're basically writing a new parallel application to broadcast the data out to node local storage. So if you have a write workload, again, if you can do per process files or some number of local files, and you just want to use it for fast local access, then you basically just redirect where you're pushing your data, and you can do that with more automated methods, or like Spectral, which will automatically synchronize at the end of your job, or something like UnifyFS that gives you the ability to do parallel access.